Today we will discuss about how to solve Cauchy initial value problem for first order semi-linear and also linear partial differential equations. So let us consider this sum y ux minus xuy equals to 0. Okay. So this is my partial differential equation along with this ux 0 equals to x square. So what is this? This is the initial data curve. Initial data actually the data is the x-axis is initial data curve as you can see here, and on the x-axis, that is on the initial data, u is taking this functional form ux is equal to x square. Okay, so I can put the I am denoting by capital gamma the data curve, so I can put it as x equals to eta, y equals to 0, and u eta then it equals to eta square. Okay, now if I consider this as my original equation, then comparing the standard form, what we will get standard form is aux plus buy equals to cxy. Okay, so you get a equals to y, b equals to minus x, and c equals to 0. Okay, so if you recall back the theory which we have learned for setting up this Cauchy initial value problem before in the last lecture, you can recall we will take now the help of the characteristic curves. That means the characteristic equations we will form. So gamma denote the characteristic curve. Okay, with parameter sigma as a parameter describing the any such curve. So x as a function of sigma, y as a function of sigma. So along this curve, the tangential direction will be given by, that means at any point on the curve P, say if you consider this is the curve, this characteristic curve. So at any point if you consider, and this curve is described by the parameter gamma. So at any point, say suppose Q, x, y, again x is a function of sigma, y is a function of sigma. So if I want to find out the direction of this tangent at the point Q, then how can you find it out? The components will be dx d sigma and dy d sigma, right? And this will actually be the characteristic equations. So that's what we are doing here. dx d sigma equals to y, that means this a, and dy d sigma equals to minus a, that is b. Now why these are taking this place, we have already discussed before, so I'm not recalling this once again. Okay, so this is the characteristic equation you get. So once you solve it, that is integrate it, you are going to get this one parameter family of curves. This is your characteristic curves family. So again, putting it in a parametric form, you can get x equals to c cos sigma or y equals to c sin sigma. You can easily see this is the parametric form satisfying or rather corresponding to this curve. Family of curves. I am saying family because if you had C, you will get one after another family member. Okay. So along any such gamma, that is any such characteristic curve, how is u varying? That is the compatibility equation. If you recall back, u is varying with respect to sigma, as by chain rule ux into dx d sigma plus uy into dy d sigma, that is equals to this one, but this is equals to 0 by equation 1, that is the original equation which is given to you, equation 1. So du d sigma ultimately turns out to be 0. So if you integrate, you get u sigma equals to c1 when c1 is again arbitrary constant. Now what we do, we find out the point of intersection, we use rather, not find out, but the point of intersection of the characteristic curves with the initial data curve. Any of the characteristic curves, you can see it is crossing here at this point, is crossing here at this point. So I consider any one of this, say P1. Okay, so let P characteristic curve cards initial data curve at the point Px1, y1. So this point is common to capital gamma and small gamma. Okay, so as it is lying on capital gamma, so and what was capital gamma? Capital gamma was x-axis, and we have already assumed the parametric form of capital gamma is like this, equation 2. So you can easily find out if for some eta equals to eta 1, x1 will be equals to eta 1 and y1 equals to 0. Again, it lies on small gamma, that is the characteristic curve. For sigma equals to 0, again sigma equals to 0. If you recall back, this is for the initial value problem thing, we are taking sigma equals to 0. It is just a convention we are following, not a logic, because we could have taken sigma equals to sigma 0. But you can easily understand this will just make these things more complex because we have to carry on the sigma 0 throughout. Okay, and we are just following the conventional thing, and if you follow any normal textbook, you will see they are considering sigma equals to 0 only. So I am following the convention. If you like, you can use sigma equals to sigma 0 also. Okay, so x1 equals to c cos 0 and c then becomes what? Equals to x1 equals to eta 1. That means eta 1 is c becomes determined, it is equals to eta 1, and y1 equals to 0 you are getting. Okay, so once you put everything here, you can easily see x1 equals to of this form, y1 equals to this form. If you recall back, we already said xy will be in the form of function of eta and sigma. Similarly, y will be also another function of eta and sigma. So that's what we are getting actually. Now let us use the Cauchy data for the u part. Okay, so let me cut it off. At p, u eta equals to eta 1 square because it is on capital gamma information we are using. Again at p, that means sigma equals to 0. As at p means now we are considering with respect to small gamma. That is a characteristic curve. U sigma equals to 0 we are putting. What do we have here? We have this one. U sigma equals to C1. So that's what we are putting. Okay. So U sigma equals to C1. But then C1 equals to, these two are equal. So C1 equals to eta 1 square. So C1 becomes determined. That's why we have what you can put. You can put here U, no need to put this sigma. U is equals to eta 1 square, right? So U equals to eta 1 square. And again, from here, from this equation, I can find out squaring and adding. You can find out x1 square plus y1 square equal to eta 1 square, right? So eta 1 equals to root over of x1 square plus y1 square. So I can put it, or I do not need the root over, I need eta 1 square only here in equation this here. So I can put directly x1 square plus y1 square. So this is your general solution. Hey, sorry, my mistake. This is the particular solution. That's what we want. That the solution which is lying in the neighborhood of the initial data curve. So uxy equal to x square plus y square. It is a particular solution which you are getting. So this is how we solve the problem, right? Now the strategy, I will work out through the strategy once we follow, or rather see another sum. It will be clear what we are doing. We already have the strategy in our mind, but just to explicitly say what exactly the steps we are following, just like an algorithm to solve a Cauchy initial value problem for the semi-linear first order partial differential equations. Okay, so first let us have a look at this sum. Okay, where this C part, you can see if you follow equation 1, you can see this is not 0. Okay, so this is your equation. This is again the initial data which is given to you. Ux0 equals to fx with x now greater than equals to. That means what? Again x-axis, but the positive portion of the x-axis. And u equals to this f of eta, that is some fixed functional form which is given. Earlier it was x square in the last sum, but now it can be any other function. But it is fixed, okay, it's not arbitrary. Okay, now again we will follow the same thing. This gamma, small gamma denoting the characteristic curve. So along the small gamma, dx d sigma equals to this y. That means equals to a, dx d sigma equals to a. And this is your a in equation 1. If you say, this is your a in equation. Okay, this is your a. It is not coming here. This is your b. And this is your c. Okay, so we are just using them here. Okay, this gives you the characteristic equation. So once again you can solve it, and you are getting this one as the one parameter family of curves, C1 being the arbitrary constant. So you can assume the parametric form, x1, x equals to C1 sec sigma, y equals to C1 tan sigma, where sigma is the parameter denoting or rather characterizing the characteristic curves. And along the characteristic curve, how is your u varying via this compatibility condition? Du d sigma equals to 2u. So from there also if you integrate, you are going to get this one. So see, unlike the previous sum, here you are having some non-zero term here. So that is giving you some change, obviously. Okay. So I can now find out C2 again arbitrary constant. So u equal to C2 into e to the power 2 sigma. Okay. Now as before, let us consider a characteristic curve cutting an initial data curve at some point P. So this point lies on capital gamma. That means you can put like this. X1 equals to eta 1 or some eta 1 now greater than equals to 0 and y1 equals to 0. Again, P lies on the characteristic curve for sigma equals to 0. So that allows us to write x1 equals to C1 sec 0. So C1 becomes fixed via eta 1. So C1 equals to eta 1 and y1 is 0. Now one thing you note, just to take care of this when you are doing the sum, here whenever we wrote x square minus y square equals to C1, we could have also written y square minus x square equals to C1. Okay, another thing I made a mistake. It will be C1 square, not C1. If I take C1, then I should have taken root over C1. It's better to take C1 square. Okay, so let me rub this out. That was saying x equals to, if I would have taken x equals to C1 tan sigma and y equal to C1 sec sigma, you could have easily seen then I would have been getting some contradictory result here. Because if I take x1 equals to C1, let me write here. x1 equals to C1 tan sigma, I would have written. Then for sigma equals to 0, that is at the point P, C1 0. But C1 is non-zero, right? Because you can easily see, and C1 0 and y1 equals to C1 sec sigma, that means C1 sec 0, that means C1, that is y1 non-zero. Okay, so this will be the creating problem because we know at the point P from here, y1 must be 0. So that means we have to take a bit care when we are forming this parametric equation, because you can change. This is because of this arbitrary constant, we can easily could have taken this one. But I need to take care of the fact what will be the x1, y1 form at the point of intersection. That means I need to take care of the initial data card provided to the problem. Okay. So again, we have formed this C1 in terms of eta 1, okay, and y1 0. So I got x square minus y square equal to eta 1 square up to this. Okay. Now at the point P, using the use part of the information, u eta 1 equals f of eta 1. But again, as P lies on gamma and u is what? U is equals to C2 e to the power 2 sigma. So you put sigma equals to 0 here. So u is equals to C2. But this one equals to, that's what I have calculated here, is equals to f of eta 1. So C2 is equals to f of eta 1. So C2 becomes determined. So u can be written, just replace C2 by f of eta 2. That means f of eta 2 into e to the power 2 sigma. That's what we have written here. Now ultimate form we need in terms of xy. Just remove the parameters. That is very easy here, because you can see from here, from this one, once eta is already determined, root over x square minus y square. What about sigma? I can easily determine sigma from the form we have assumed. That means what we have assumed, x equals to C1 sec sigma, y is equals to, x equals to C1 sec sigma, y is equals to C1 tan sigma. So from here I can get out or take out the sine sigma. That means sigma is equals to sine inverse of y by x. So this I can use where? Here in this form. Eta 1 is replaced by root over x square minus y square. And you see I have taken the positive part only because it is given eta 1 greater than equal to 0. So I won't take into consideration the negative part. So that's why I have taken root over x square minus y square e to the power 2 sigma, where sigma is replaced by, I just have to complete it by writing sine inverse y by x. So this is your required solution, particular solution surface in the neighborhood of the initial data card capital gamma. Okay. So from the two sum, now we have the idea that we can put these steps all together. So what we are actually doing for any sum up to semilinear, I am forming dx d sigma dy d sigma. From here I am integrating to get the one parameter family of characteristic curves. So from here I can again write the parametric form as this one, some function of sigma c1, g1 function, g2 function, and using the compatibility condition I can write g3 function of sigma c2. That means I can write u as g3 sigma c2. Okay. Now intersection point I will use. What is the intersection point of gamma and capital gamma and small gamma? That is the characteristic of initial data curve. Okay. That's why from here, if you recall back, we already said this characteristic curve should not be, or rather I should say the initial data curve should not coincide with any characteristic curve. Okay. That was the condition for the existence of solution of Cauchy initial value problem. I said it, if you recall back in the first lecture. Okay. So here as P1 is on capital gamma, that is a characteristic, sorry, initial data curve. I can write like this: x1 equal to some function of eta 1, y1 some function of eta 1. Okay, eta 1 is some fixed value of eta. Okay, that means I am taking some fixed value. I am taking just using the symbols eta 1 as we have did in the sums also. And again, it is P1 is on small gamma. That means x1 is equals to g1. G1 was the form, this form. Sigma just put 0. So G1 0 C1 and Y1 G2 0 C1. So using this 4, what we are doing? We are finding out G6 some function of x, y, eta 1. Okay. So from here, I can easily find out x as some function of from here and also from this one, which is given to us here. Okay, that means actually what we are doing from here, where if we just recall back what we did in the sums, we replace the C1 somehow, the arbitrary constant. I replaced it by the function of eta 1 xy. Okay, and then using this one, I can ultimately write x as a some function of sigma eta 1, y as some function of sigma eta 2. So from there again, sigma can be obtained as a function of xy. Now let us come to the u part of the information. U is equals to some function of eta 1 at the point P, because it is on gamma, something was given to us, the initial data. So let me call it G9 function. I am naming the function as G9 of eta 1. And again U, G3, 0, C2. From where we are getting, we have already put that thing here, that's why this one. G3, sigma, in place of sigma you put 0, so G3, 0, C2. So that is equals to here, and this 2 will be equal. So from there I can replace C2 by some function of eta 1. So you just put this C2 here. So U is equals to G3 sigma comma C2 was there, right? In place of C2 I am writing this one, which I have already obtained. Okay, so that gives me some function of explicitly in form of sigma eta 1. Now sigma eta already coming in forms of xy, so you just put everything here to find out uxy as a function. U is equals to uxy. So this is your particular required solution surface. Okay, so this is a main strategy, right? I have included two other sums. You can simply follow it here. Just I am given the hint, right? Actually, I'm just giving the hint so that you can just simply follow it out and just see how we are solving this sum. So here the initial data curve is again x-axis, and as you can easily see, I have not written this all the steps explicitly. Hope it will be clear to you from the following last two sums. So I'm just simply shown you the steps from where, again following the same strategy, you are going to get this as your solution. Okay, exactly the same strategy we are following, and also for this sum. Here also we are doing the same. This one, same thing. Parametric form I am using. This is the gamma curve, and this is the u portion, and this is the point of intersection. At the point of intersection, again, this C1 gets determined, C2 gets determined, and ultimately everything you put together, you ultimately find out eta 1 in terms of xy, as I said, the strategy, and also sigma from here, again in terms of xy. Okay, and then you again put everything here in equation 4. Sigma derived in xy, you put it here. Eta 1 derived in terms of xy, you put it here. So everything comes out. So this solves the problem. Okay.